Gasoline can be replaced with overhead electric wires that enable vehicles to accept electric power as they're driving down the road, so that they can recharge their batteries and use the power at the same time. For the United States, there are about 400,000 miles of highway, allowing 5 lanes per each highway average. There's at least 4. That would be 2 million lane miles of highway. In addition, the continental United States is about 3 million square miles. If one wants to have a road every 10 miles by 10 miles, that's 100 square miles. But on each extension, you have to add 2 outer edges of 10 miles each. So across the United States, that would come up to about 1 road for every 5 square miles, or about 600,000. The highways are 400,000 miles, allowing for inconsistencies and some need for repetition that might produce an additional 400,000 miles of county roads might be needed, allowing 2.5 lanes on average for each county road, at least 1 in each direction. That's another 1 million miles. Plus the 2 million is 3 million. Then you have local streets. There are 300 million people in the United States. If you say an average of even 10,000 people per square mile, it should be higher than that, that's 30,000 square miles. There's at least 2 lanes necessary, 1 in each direction, and then it depends how many specific roads you want to have per each square mile. Overall, maybe 300,000 miles would be necessary. So a total of 3.3 million lane miles would be necessary. At $300,000 per lane mile, that would come out to a cost of $1 trillion for building the electrified lines above roads. At 6% interest, that would be $60 billion per year. Allow another $60 billion for maintenance, and there's about $120 billion for maintaining the overhead lines. There's about 180 billion gallons of gasoline and diesel used per year. So that comes to about the equivalent of 70 cents per gallon. A gallon of gasoline produces about 12 horsepower hour, or about 9 kilowatt hours of power. Allow for some inefficiency and say 11 kilowatt hours would be needed. The cost of electric power is all over the map. There's one estimate that says 6 cents for fossil fuels, 8 cents for wind, 10 cents for nuclear. Wind can be as low as 4.5 cents with high wind areas. But up in New England, you're looking at costs of 16 cents or more for generating per kilowatt hour. But if you take a cost of 10 cents per kilowatt hour, plus an additional 6 cents for distribution costs, it's 16 cents per kilowatt. If you're using 11 kilowatts per gallon, that's $1.76. Plus the additional 70 cents for the actual transmission lines, the power lines overhead, and that comes up to about $2.50 per gallon, which is comparable to the current production cost of gasoline. It is possible to replace gasoline with overhead electric lines for about the same cost. Taxes, of course, would be extra, and there would need to be a source for taxes. There's also the question of how you'd actually collect payment for the electricity, which could get complicated. The pantographs that would be raised above the car are also have to be considered. If a car weighs 3,000 pounds and its center of mass is 2 feet above the ground level, then you're looking at 6,000 pound-feet overturning. The center of mass of the pantograph would be at least 10 feet above the ground. If you wanted to increase the total overturning potential moment by no more than 10%, the pantographs would have to weigh less than 60 pounds or less. That might be achievable with composites. The other factor is side wind. With the side wind blowing, there's going to be an overturning force on the pantograph. If air is blown up through hollow shafts and out through small holes, that could help in streamlining both in forward direction, and if a wind comes from the side, the air being blown up, less would come out on the side of the wind, more would come out opposite, and that would also help to reduce the overturning moment. For the actual power, you would look at trucks. A truck needs about 300 horsepower, or about 220 kilowatts of power. Allow 240 kilowatts, which is 240,000 watts. If you have 6,000 volts, that would mean 40 amps would be required. If you space trucks, which could be up to 85 feet long, every 100 feet, which is closer than they should normally be operating, that's 50 trucks per mile, give or take. Times 40 amps is 2,000 amps total. The average distance would be 1/2 mile if you're spacing them, the transformers every 2 miles. The vehicles would be no more than 1 mile away. That would be 1,000 amp miles. The overhead wire material is known as trolley wire. The heaviest currently available is 6,000 pounds per mile. You might want to go to a 12,000 pound per mile. At 6,000 pounds per mile, its area is about 1/4 of a square inch. At 12,000 pounds, you'd have 1/2 of a square inch. For 1,000 amp miles, at the half square inch, the factor would be about 0.2, or about a 200 volt drop would be required. That would be adequate against 6,000 volts. The density of current at half a square inch would be 4,000 amps per square inch, which is a bit high, but it's unlikely to have that much usage on any sustained basis, so it might be acceptable.